board here. Colligative properties just has to do with the properties that depends. Those are the properties that depends on the ratio of the number of solid particles to the number of solvent molecules in a solution, and not on the nature of the chemical species. I think we have to highlight that info there. There's some important key concepts that you have to take note of. We have said that colligative properties are properties of solutions that depend on the ratio of the number of molecules of the solvent, that is the number of solvent particles, to the number of solvent molecules. So you are just dealing with ratio of the solute particles, the number of solute particles, to the number of solvent molecules, and not on the chemical species, that is the nature of the chemical species present. That's just what we mean. That's what we mean by colligative properties. So very important. When they ask you in your exam what are colligative properties, you just have to highlight these important points. These are properties that depend on the ratio of the number of solute particles to the ratio, that's to the number, I said ratio already, to the number or the molecules of the solvent. I get it, and not on the nature of the chemical species. That's what we mean by colligative properties. So colligative properties do not have business to do with the nature of the chemical species. You get, it's just depending on two things, which is the solute particles and the solvent molecules. Now, in general, we have 4 colligative properties. We have 4 colligative properties. And what I think we have vapor pressure reduction, we have boiling point elevation, or is it increase in boiling point? Then we also have your freezing point depression, and finally osmotic pressure. So those are the 4 colligative properties that we have. We have your boiling point elevation, freezing point reduction, vapor pressure reduction, and osmotic pressure. I will be explaining all this in details. So starting from the first colligative properties, vapor pressure reduction. Actually, your vapor pressure reduction has a lot to do with your Raoult law. Raoult's law is what enables you to be able to approximate the number of the amount of vapor pressure of the solid over the solution that should be required. Are you getting me now? So now, why is vapor pressure reduction a colligative property, or how is it a colligative property? And we have that on the board there. It says that the sheer presence of solute lowers the number of solvent molecules. It lowers the number of solvent molecules coming and going out, therefore lowers the equilibrium vapor pressure. Now, one thing you must know, basically and generally, is that when you have a solute, I get me now, sorry, solvent, and you heat it up, there will tend to be evaporation. I get me now, there will tend to be vaporization or evaporation. I get me now, and it occurs from the molecules at the surface. Now, the moment solutes are passed into it, the moment you have solutes passed into that solvent, what happens? It begins to block the solvent molecules at the surface and makes it difficult for the vaporization to take place. And that process is what we call vapor pressure reduction. And that's what we're talking about here. So we said the sheer presence of the solute lowers the number, that solute that was added into the solvent. It lowers the number of solvent molecules coming and going out, which I just said. Why? Because they occupy the surface. Are you getting me now? They block the molecules at the surface. Are you getting me now? Therefore, making it difficult for the solvent molecules to quickly vaporize. Now, the whole of that process can be explained through Raoult's law. I get it now. That's what we wrote here. We said Raoult's law enables us to obtain an approximate of the vapor pressure. To obtain an approximate of the vapor pressure of solvent over the solution of the solvent over the solution. So that's what vapor pressure enables us to obtain. Now, what does Raoult's law state? Now, Raoult's law states that, that's what you have here. Raoult's law states that what? That the vapor pressure of a solvent over a solution, the vapor pressure of a solvent over a solution is equal to the product of the mole fraction of the solvent. Please take note. This time around, no mole fraction of the solute. We'll be calculating the mole fraction of the solvent over the solution and the pressure of the pure solvent. Now, the pressure of the pure solvent is that pressure that will be obtained when there are no solids present in that solution. That's really just like the pure solvent. That would have been, for example, now, a pure solvent can actually have a vapor pressure of 2 atm. Are you getting me now? I have a vapor pressure of 2 atm. But the moment you pass in solids into it, those solids that you pass into it causes the vapor pressure to reduce. I get it now. That's why we say vapor pressure reduction. Now, how does that reduction occur? We said that the vapor pressure of the solvent over that solution, that means that solvent over the solution which contains the solid, I get it now, is equal to the product of the mole fraction of the solvent over the solution and the pressure of the pure solvent. So this is an expression. We have an expression here to demonstrate that. Here, your P solvent is the vapor pressure of solvent over solution, and X solvent is your mole fraction of the solvent, which will be mole of solvent over the mole of the solution, which is the total mole of solution. You can obtain that by saying the mole of the solvent plus the mole of the solute times the pressure of the pure solvent. We'll be solving questions on that soon, but we have some limitations to Raoult's law, like concentration. I'll be exploring how concentration serves as a limitation to Raoult's law in later lectures. Now, decrease in freezing point. Decrease in freezing point. Now, what I want you to understand first is what is freezing. In our phase diagram, we know that freezing just has to do with the transition of a liquid phase of matter into a solid state of matter, and the reverse is called melting. The conversion or transition of a liquid state of matter into a solid state of matter, that's what we call freezing. You can take note of that. Now, what we should remember here is that freezing point is the temperature at which a liquid becomes solid at 1 atm. At 1 atm, that's the standard and pressure. So that's the meaning of freezing point. Freezing just means transition from liquid phase to solid phase. But when you say freezing point, like to obtain the freezing point of a substance or of a matter, is obtained, or you can say it is that point where the solid phase and the liquid phase coexist, or are at what? Equilibrium, given that the atmospheric pressure was 1 atm. That's what we're trying to say. So we said that we call freezing point. Let's bring it closer. We said that freezing point is the temperature at which a liquid becomes solid at 1 atm, or you can say it's the temperature in which solid and liquid phase coexist. Are you getting me now? Where they coexist. Now, one thing again you must take note of is that as temperature lowers, normally the solution becomes more ordered as it moves toward the solid phase. Now, that's something very important. Okay, I can see you. Welcome. Now, we said before you joined in, I've already gotten to the decrease in the freezing point. We talked about solution, colligative properties. If you watch the lecture, you obtain to understand all those things. From here, you can actually still grab the knowledge. Now, decrease in freezing point. How is it a colligative property? That's what we're trying to see. How does addition of solid to a pure solvent affect the freezing point. And we said it's affected by reducing the freezing point. So we now want to check how this thing happens. Why do you add solute to a solvent and it ends up reducing the freezing point? That's what we're trying to obtain here. Now, normally for transition to occur, for freezing transition to occur, one of the things that basically happens, you must take note of, is that there is an increase in the orderliness of that matter. When you move from liquid to gas, remember that orderliness is just as a result of proper arrangement or compactness of the molecules of matter. And it is important for you to remember that when you hear the word entropy, entropy simply means, that's what you call S. Entropy simply means the degree of randomness, the degree of randomness of a system. And you agree with me that when you say the degree of randomness, that's, you can say, the degree of disorderliness. And naturally, the world tends to move in a disordered manner. Everything about nature is tending to increase entropy. If you should leave an environment right now and you come back, you can't see the environment cleaner than the way it was. Rather, it will be what? More disorganized than the way you left it. Just like that nobody touched it. What that means, nature is showing you its ability to increase entropy. Now, what we now pointed out from here now is that as temperature lowers, the solution becomes more ordered, which I just explained to you now. As temperature is lowering, entropy, that is, the molecules becomes more ordered. Why? Because they are tending to become solid. Becomes more ordered as it moves towards the solid phase. You know, for you to freeze something, you are lowering temperature. I get it now. So the temperature will continue to lower, I get me, until it turns to solid. And that point where it turns to solid, that's where the liquid and the solid phase coexist. Next point, I get me now, will lead to solid phase, is what we call the freezing point. So that means there needs to be decrease in temperature for you to obtain your freezing point. Now, we now say that as that temperature is lowering, something is happening. The molecules are becoming more ordered because they are trying to become solid. And when you say they are trying to become more ordered, note to us that entropy means disorderliness. We now say that means that entropy is decreasing. It means that entropy is what? Is decreasing. Now, since entropy is decreasing, when you add a solid, I get it now. When you add a solid to that solvent, what happens is that the entropy increases. That means the amount of disorderliness increases by addition of what? Solid. In the way you add solid to something, you have actually disorganized it. So it becomes more disorganized. And when it becomes more disorganized, that means you are saying that the entropy has increased. Remember that the aim for you to get your freezing point is your ability to reduce entropy. That means reduce disorderliness. You're trying to organize. So entropy is there to disorganize. I get me now. So when you add solids, you are automatically increasing entropy. The molecule becomes more disorganized. Thus, you need to reduce temperature the more, so as to what? So as to remove the effect of that entropy. I get it now. To annul the effect of that entropy increase. So that's what we need to think about. So we said adding a solid increases the entropy. Thus, to overcome the additional entropy, the temperature will have to be lower than normal. So that means normally if the solvent is supposed to have a freezing point of -5, if you should add solid to it, it becomes more disorganized. I get it now. So to organize it to be more harder, so you have to go lower. Since lower temperature is what organizes the molecules. So that excess of entropy that needs to be organized, I get it now. That excess of entropy effect on the molecules that you will now need to organize is what's responsible for us seeing a decrease in freezing point. I get it now as equivalent because you need to decrease the freezing point than normal. I get it now. So there is a formula that enables us to obtain the change in the freezing point. Obtain the change in the freezing point, and that's this formula we have here. That's this formula we have here. We say change in TF is equals to I K subscript FN. Now, when your change in TF is standing for your what? Is standing for your change in freezing point. Change in freezing point. That's what it means. Then your I here is known as the Van Hoff factor. The Van Hoff factor. I get it now. And this Van Hoff factor is just the number of particles into which the solute dissolves. The number of particles into which the solute has dissolved. Then Kf here stands for your molar freezing point constant, or you can call it the freezing point depression constant. I get it now. Freezing point depression constant. Then change in your TF, I've said that. Then M here is standing for your molality. M stands for molality. Molality, that's what it stands for. M is molality. Remember, we said molality just simply means the number of moles of the solute over the kilogram of the solvent. So that's that for freezing point. Freezing point, the mechanism of this freezing point I just explained now is associated with the second law of thermodynamics. And I'll be explaining that concept more when we get to thermodynamics, as we're talking about thermochemistry or thermodynamics and physics. Now let's now come here. The next colligative property we have is your increase in boiling point. And if I may ask, what do we mean by boiling point? What do we really mean by boiling point? You remember that? Now, boiling point simply means the temperature at which the vapor pressure is equal to the atmospheric pressure. Vapor pressure is equal to the atmospheric pressure. Now, let's now imagine this. Let's see why we said increase in boiling point. Let's imagine something at the normal boiling point. The solvent, the pure solvent, at the normal boiling point of 100 degrees Celsius, just like water. Now, it means that it is at 100 degrees Celsius that the vapor pressure of water used to be equal to the atmospheric pressure. Now, when you add a solute to that pure solvent water, we said that there will be a decrease in the vapor pressure. True or false? That's the vapor pressure reduction. Said the vapor pressure will reduce. Now, when the vapor pressure reduces, it means that water has to continue increasing its temperature so that that reduction can be overcome. I get it now. So in the process of water increasing its temperature, I get it now, automatically it will have a higher boiling point. That means the temperature will have to move high enough to be able to push that vapor pressure to get in alignment with the atmospheric pressure. It's a very, very easy phenomenon. Water is 100 degrees Celsius. You add a solute. Adding the solute, we know that the vapor pressure will reduce. And when the vapor pressure reduces, and we know that the vapor pressure reducing, we know that for water to reach its boiling point, the vapor pressure has to be equal to the atmospheric pressure. Remember, atmospheric pressure will not change. So vapor pressure reducing as a result of addition of solute, we now need boiling point of water to actually continue going up. Why? Because you have to push that vapor pressure to increase until it is now the same atmospheric pressure. And that process is all called increase in the boiling point. And that's the phenomenon we have here. So just for you to be able to write it down. So we have on the board, we said that adding a non-volatile solid to a solvent increases the boiling point. This is due to decrease in the vapor pressure, which will have to be elevated in order for boiling point to be attained. And now that's because boiling point is the point where vapor pressure is equal to the atmospheric pressure. So meaning that when you add solid, we know vapor pressure reduces, and when that vapor pressure reduces, for you to get to the boiling point of that substance, it means that we need to continue increasing the temperature. I get it now. So as I increase the temperature, the vapor pressure will continue to increase. until it now merges back with the atmospheric pressure, and that will be at a higher temperature. That higher temperature is what we call change in CV. Are you getting me now? Are you getting now? So the change in that temperature is what we call change in CV. Are you getting that? Change in boiling point. Change in boiling point. Yi is still our Van Hoff's factor, which we said is the number of particles into which the solute dissociates. And M here is your molality. M is molality. So that's that for that. Now I want to go to the last colligative property, which is osmotic pressure. Now, osmotic pressure just simply means it is that applied pressure required to prevent the movement of water from solvent to solution. Now, let's try and recall what is osmosis. Osmosis just simply means the movement of particles, so substances, ions, atoms from a region of what? Lower concentration to a region of higher concentration. Are you getting me now? From lower concentration to higher concentration. Now, when I say osmotic pressure is that pressure that is applied in order to prevent the movement of water from solvent to what? To solution. To prevent the movement of water from solvent to solution. Now, why is osmotic pressure a colligative property? Osmotic pressure is a colligative property. Why? Because it actually shows relationship, proportionality, variation, are you getting me now, with the number of moles or concentration. That shows that osmotic pressure is circular to be referred to as a colligative property. Are we getting that now? So that, let's now look at a formula that we can use to relate our osmotic pressure. Now, do we remember this? PV equals to nRT. PV equals to nRT. Let's just divide both sides by V. So when we do this, we are having P, or V capital V, equals to nRT over V. Now, we can also recall that our molarity is equal to number of moles over volume. So we can substitute that into this place, and we'll be having P is equal to nRT. Now let's change this P, this pressure here, to atmospheric pressure now, not to osmotic pressure, not gas pressure. Let P equals to this. This is the symbol. This is the symbol for your osmotic pressure. So we're saying that our osmotic pressure is equal to nRT. That's what's the formula for our osmotic pressure. So that's that for that. Now we'll be solving some problems on the concept. Are you getting out? We'll be solving some problem on the concept. And that is where we'll call it day for that topic. We'll call it day for the topic. Very, very straightforward. And let's look at some questions. Let's look at some questions on that topic. Okay. We'll be solving a number of questions from the concept we've just dealt with. Okay, first question says, first problem says, that we should calculate the vapor pressure lowering. Calculate the vapor pressure lowering, which is called change in P. When 10 ml of glycerol, which is C3H8O3, is added to 500 ml of water. At 50 degrees Celsius. At this temperature, the vapor pressure of pure water is 92.5 torr. At this temperature, the vapor pressure of water is 92.5 torr, and its density is 0.988 gram per milli, and its density is 0.988 gram per mil. To stop, and the density of glycerol is 1.26 gram per mil. So that's that for that one. Let's now look at another question. Look at the question from all these are boiling points and then lowering and increasing of this. So this next one says, problem 2. It says you add 1 kilogram of ethylene, you add 1 kg of ethylene glycol, which has the formula of C2H6O2 antifreeze, to your car radiator. Which contains 4450 gram of water. Then they said, what are the boiling and freezing points of the solution? What are the boiling and freezing points of the solution? That's that question for that. And one last one we'll be doing. Will be from osmotic pressure, and that one says, is 0 points at problem 3. Is 0.30 molar solution of sucrose at 37 degrees Celsius has approximately the same osmotic pressure as blood. The same osmotic pressure as blood. What is the osmotic pressure of blood? What is the osmotic pressure of blood? So that's it. Is that a question we're going to be solving right now? I believe you have them handy. These are three questions. These three questions are covered the four different colligative properties that I've talked about. So let's solve them. Solution. The first one says, and people are not writing them. The first one says, calculate the vapor pressure lowering when 10 ml of glycerol is added to this ml of water. Automatically, the first thing that comes to your mind is which one is the solute and which one is the solvent. So, answer number one, our solute, our solvent. So, which one is the solute here? The solute is glycerol because that's what you added to water. So, water is the solvent, H2O. Are you getting that now? Water is the solvent. I believe you've written the question down. And glycerol is the solute. Now, 10 ml, they said 10 ml of glycerol. That means the volume of glycerol was 10 ml. That was, they added 10 ml of glycerol is added to 500 ml of water. So the volume of water it was added to was 500 ml. Okay. At 50 degrees Celsius. The temperature was 50 degrees Celsius. At this temperature, the vapor pressure of water is 92.5 torr. At this temperature, the vapor pressure of water is 92.5 torr. Water is the pure solvent. So you are saying of the solvent, 92.5 torr. Are you getting it now? And its density is 0.988 gram per mil. Density 0.988 gram per mil. That is of water. You understand? I was talking about water. They said the vapor pressure of water is this and the density is this. Then they gave the density of glycerol. They said that the density of glycerol, so of water, is equals to 1.26 gram per mil. Okay. Now we know that to obtain this change in pressure, we're applying Raoult's law because it's Raoult's law that tells us that this of that solvent, solvent equals to mole fraction of the solvent times the pressure of the pure solvent. That was told to us by Raoult's law. Okay, so we have to look for this. Once we have this, we already have this value here, which is 92.5 torr. Once we can get this, that'll be all. But how do we get mole fraction? We know that mole fraction of solvent is equals to what? Is equals to the mole of that solvent. Since I say mole fraction of solvent, mole of solvent over mole of solute. And you can get the mole of solute by saying mole of solvent plus the mole of the solute. Okay, so now, what's our mole of solvent here? How can we get it? Let's get this mole. density, remember that density, recall that density is equal to mass over volume. I get me now, and they've given us everything in middle, so we don't need to convert. So let's get the mass. That means mass itself is equal to density times volume. So you can say mass of glycerol, the mass of glycerol will now be equal to how many? That will be equal to volume of glycerol, density of glycerol times volume of glycerol. What's the density of glycerol? 1.26. What's the volume of the glycerol? 10. So that tells us that our mass of glycerol is equal to 12.6 grams. Are you getting that now? And what we need actually is the mole. So what formula for mole? Or let's first get the mass of water also. Let's come here and get the mass of water. So we know that mass of water, we know is equal to density of water also and volume of water. This is where we recorded our water values. You can see there, here we recorded our water values. So you can see here that our density of water was given to us at 0.988 gram per mole. So 0.988 gram per mil times the volume of water given was 500 mil. If you check, 500 mil. Are we getting that now? For 500 mil, and if you point that into your calculator, you should be having a value of that's giving you a value of not the calculator here. Okay, let's just say that this is the mass here. You know that this is the mass, we solve everything together. Okay, so when you multiply this, whatever it gives you is your mass. Now, we now recall also that mole is equal to mass over molar mass, because that mole we need. So what will be the mole of glycerol? Mole of glycerol equals to mass of glycerol over molar mass of glycerol. And we got the mass of glycerol before we check when we add 12.6 grams. And glycerol was given to us. We know the formula of glycerol. It says C3H8 O distance. So that's C3, 12 times 3, 36 plus 8, that's 1 times 8, 8 plus oxygen, 16 times 3, 48. And that gives us a value of what? When you point that to your calculator, you get the mole. That's giving us the value of 0.137 mole. 0.137 mole. So that's the mole of glycerol. What about the mole of water? Now the mass of water, and we got the mass of water as this. I've not multiplied them through. This is the mass of water, 0.988 times 500 divided by the molar mass of water. You know, mass over molar mass. Molar mass of water is 18 H2O. That is 2 plus 16, 18. And that will be giving us a value of 27.4 mole. 27.4 mole. If I'm not mistaken. If I'm not mistaken. 27.4 mole. Okay. Now that we have that, we can now get our mole fraction. We say mole fraction of the solvent is equal to, we said mole of water, because water is solvent, that's 27.4 over the mole of the solution. The solution is the solute and the solvent together. So we're saying 0.137 plus 27.4. Are you getting that now? And that will be giving us a value of sorry, we are supposed to make use of the mole fraction of glycerol. Because the question said that at this temperature the vapor pressure of water is that, and your formula for this thing for mole fraction is the solute, that is glycerol. Sorry, glycerol. I corrected it here right now. Glycerol. You get. So 27.4 over this, and it will be giving us a value of 0.00498. 0.00498. So that means that our pressure change will be equal to, remember we said is mole of glycerol times pressure of water in pure solvent. So we're having this is our value here, 0.00498 times the pressure of H2 that was given to us, that is the pure solvent, which is 92.5 torr. Are you seeing there? 92.5 torr. So that gives us a value of functional in the calculator, which obtains 0.461 torr. So that's our answer to that question. That's our answer to that question. Very, very straightforward and very, very easy. Okay, so we now move on to the next problem. Problem number 2. All you need to remember is your Raoult law formula. That's all you need to remember. We're told that when this amount of glycerol is added to 500 ml of water, so basically you now get the mole fraction. Mole fraction there of glycerol is what we're getting. Okay, they said you add 1 kilogram of ethylene. I believe you wrote the question down. You can pause the video to write this question down. You add 1 kilogram of ethylene glycol and antifreeze to your car radiator, which contains 4450 grams of water. Automatically, our solute is the ethylene glycol, which is C2H6O3, okay, O2. Then we also have our solvent, which is water again, because they said the radiator which contains a small amount of water. Now, you added it to your car radiator, which contains this. They said it contains 4450 grams of water. So we're saying mass of your solvents, I get it now, which is your mass of your water, is equal to 4450 grams. I get it now. What are the boiling and freezing points of the solution? Remember that it said it was 1 kilogram of ethylene glycol. So your mass of ethylene glycol is 1 kilogram. I get that now. It's 1 kilogram, which is equivalent to 1,000 grams. Now, we know that the formula we're going to apply here to get, if we are getting for both boiling point and freezing point, we know that our change in temperature for boiling point is equals to IKF and IKBN. That I is negligible, so we can just say KBN. For your level now, you will not be applying that I. You will not be applying the I. Okay. We have to get the molality first. We're giving our KB. We're giving the KB. The KB was given to us there. KB was given to us 0.512 degrees Celsius per m. KB was given to us, KB. This should add that to the question it was given. Your KB, let me write it here. In the question, your KB 0.512 degrees Celsius per m, and your KF was also given, and that is 1.86 degrees Celsius per m. 1.86 degrees Celsius per m. So that's the value there. So we're just going to be applying that now. So let's look for our M, molality. Remember, molality is equal to what? Mole of solute over kilogram of solvent. So how do we get our mole of solute? So we're saying molality is equal to mole of solute. And our solute is this. So the number of mole of solute, mass over molar mass. Mass is 100. Molar mass, this 12 times 224 plus 6 plus 16 times 232. And that will be giving us a value of what? If you put that into your calculator, you should be obtaining a value of 3.62. 3.62. 3.62 molality. So that means our change in TB, our molality, that's our mole of this. So our molality will be equals to mole of solid, which is 3.62, all over kilogram of solvent. All over kilogram of solvent. Sorry, this will be 16.1. This will be 16.1. 16.1 mole. 3.62 over, sorry, 16.1 over kilogram of solvent. Our solvent is this in gram mass. But convert to kilogram divided by 1,000, 1, 2, 3, that's 4.45. And that will be giving us a value of 3.62. 3.62 M. So now we can now get our change. Can now get our change in TB. Can get our change in TB. So our change in TB will now be equals to molality, which is 3.62 times our Kb, which is 0.152. And that will be giving us a value of 1.85 degrees Celsius. 1.85 degrees Celsius. But the question says to find the new boiling point. So the new boiling point will be equals to the boiling point, that is the new boiling point TB2 with TB1 plus that change in TB. But we know why we adding the change, because we know that boiling point elevation to increase by this factor, this is the change. So our normal boiling point of water is 100 plus 1.85 degrees Celsius. Normal boiling point of water 100, change 1.5. So that gives us 101.85 degrees Celsius. That's our new boiling point when you pass the ethylene glycol. The same process applies for your TF. Our change in TF is equals to KFM, and that is change in TF will be equal to our KF was given to us as 1.86, and our molality, we've gotten that our molality was 3.62, and when you punch that into your calculator, you have a value of 6.73 degrees Celsius. 6.73 degrees Celsius. So that means our new freezing point, CF2, new freezing point will be CF1, normal freezing point of water is 0 degrees minus the change in TF. Why am I minusing? Because I know that it is decreased. There is a decrease in freezing point. Freezing point is depression. So our final this will be equals to 0 minus 6.73 degrees Celsius. So the new freezing point will be minus 6.73 degrees Celsius. That's for that. That's that for that. Then finally, we'll be looking at our final question, problem 3, solution to problem 3. And it said a 0.30 molar solution. So our molarity was given to us as 0.30 molar solution. And it gave us the temperature there, has an approximately the same osmotic pressure as blood. What is the osmotic pressure of blood? What is the osmotic pressure of blood? We know our formula is your this equals to MRT. They gave you our temperature in that question as 37 degrees Celsius. But we know that temperature will now be equal to 37 plus 273. And when you do that, you should be getting 3. Is it 3 again? Yeah, it will be 310 Kelvin. 310 Kelvin. So we'll be having vapor pressure, which is the pressure now. Osmotic pressure rather will be equals to 0.30, that's going from times R, which is 0.0821, times your temperature, which is 310. So automatically our osmotic pressure will be having a value of I'm not mistaken, we're having a value of this. I don't know, where's the calculator around here? Let's see if we can do this. 310 times 0.3. So, okay, approximately anyways, whatever you have here is your answer in it's here. Whatever you have there is your answer in here. The calculator is not available right now. Has been taken away. So that's all under your lecture 2. With that, we are done with everything under our lecture 2. We're done with everything under our lecture 2. So anywhere you have a problem or question, feel free to ask me and we will actually respond to the question. You can also solve more questions on this aspect. If you're interested, I can help you with more questions. So make sure you stay tuned. This is Guaranteed Professional Tutors. And once again, I'm Dr. Henry. Good day once again. Welcome to Guaranteed Professional Tutors. I'm Dr. Henry, and today we are going to be talking about dealing with chemistry 002 lecture number 2, part 2. And that's where we'll be exploring information on our colligative properties. So, basically, what do we really mean by colligative properties? I have this written on the board here. Colligative properties just has to do with the properties that depends, those are the properties that depends on the ratio of the number of solid particles to the number of solvent molecules in a solution, and not on the nature of the chemical species. I think we have to highlight that info there. There's some important key concepts that you have to take note of. We have said that colligative properties are properties of solutions that depend on the ratio of the number of molecules of the solvent. That is the number of solvent particles to the number of solvent molecules. So you are just dealing with ratio of the solute particles, the number of solute particles to the number of solvent molecules, and not on the chemical species, that is the nature of the chemical species present. That's just what we mean. That's what we mean by colligative properties. So very important. When they ask you in your exam what are colligative properties, you just have to highlight these important points. These are properties that depend on the ratio of the number of solute particles to the ratio, that's to the number, you know, I said ratio already, to the number or the molecules of the solvent. I get me now. And not on the nature of the chemical species. That's what we mean by colligative properties. So colligative properties do not have business to do with the nature of the chemical species. You get, it's just depending on two things, which is the solute particles and the solvent molecules. Now, in general, we have 4 colligative